In this recording, we'll work a few momentum problems. Okay, let's look at the situation here. What we have two blocks connected by a spring and tied with a string. It is a frictionless surface. The spring is light, does not have much mass. That's the idea of saying light. And the spring is compressed. So the cord is holding them together with the spring being compressed. Now when we cut the cord, because the spring is compressed, the masses are going to move apart. 3m is going to move towards the right, and obviously m is going to move towards the left. So they tell us the speed of the 3m mass. They say it's 2 meters per second. And they're asking us the speed of the block of mass m. Okay, now the situation here that we have to think of, we had two cases. We had the masses held together, and then the string breaking, they are going to move apart. So somewhat it's like an explosion. So we have to worry about the momentum before the explosion and the momentum after the explosion. And both of these momenta should be equal since we don't have external forces on the system. Now, momentum before, it's going to be 0 since neither of the masses is moving. So that's good. Momentum after. Momentum after is going to be equal to the momentum of the 3m block plus the momentum of the m block. Now, the momentum of the 3m block is going to be the 3m mass times plus 2 meters per second if we take that direction as the positive direction. And the momentum of the m block is going to be m times the velocity of the block that we don't know. Okay, so now, and this should be equal to 0, which means I have 3 times m times plus 2 meters per second plus mv equal to 0. And I'm solving for v, so I'm going to move this to the other side. So I have minus mv is equal to 3m times 2.00 meters per second. I'm going to divide both sides by m, so the m's cancel out, and we are left with minus v equal to 3 times 2 meters per second, which is 6 meters per second, which means v is minus 6 meters per second. So that tells us it's going to move this way at 6 meters per second in this direction. The negative sign tells us that it is moving in that direction. Okay. Now, this is another question. We have a car that it is moving with an initial speed of 25 meters per second towards the east. So let's call this the east. Okay, and we have a truck that's moving at 10 meters per second this way. Okay, and the car is moving at 25 meters per second this way. Okay, the car is going to rear end the truck. After the collision, they tell us that the car is going to be moving at 9 meters per second, still towards the east. And the question is, what's the velocity of the truck? Okay, again, momentum before should be equal momentum after. Momentum before the collision is momentum of car plus momentum of truck. Okay, now what's the momentum of the car? It's 25 1,000 kilograms. I took too much space with these graphics. So 1,000 kilogram times 25 meters per second. That's the momentum of the car, plus the momentum of the truck, which is going to be 9,000 kilograms. Since everything is moving in the same direction, that makes it easy here, times 10 meters per second. So I have here 25,000 plus 90,000, which should give me 115,000 kilogram meters per second. That's my momentum before the collision. That should be my momentum after the collision. Okay. My momentum, oops. Okay, let's go here. A mishap. Momentum after the collision should be that same 115,000 kilogram meter per second. Now, what's the momentum of the car after the collision? Momentum of the car after the collision is the mass of the car, 1,000 kilograms, times the 9 meters per second. So it is 9,000 kilogram meter per second. The momentum of the truck is just the mass of the truck, 9,000 kilograms, times my unknown v. The sum of these, 9,000 kilogram meter per second, plus 9,000 kilograms times v, should be equal to my combined momentum after, which is 115,000 kilogram meter per second. We are solving for v, so 9,000 kilogram times v is going to be 115,000 minus 9,000. So 115 minus 9,000, that gives us 106,000 kilogram meter per second. And then my v is then 106,000 kilogram meters per second divided by 9,000. That gives us 11.8 meters per second. That's the velocity of my truck. Okay, a few conceptual questions. We have two identical balls that are dropped from the same height onto the floor. Okay, two identical balls dropped from the same height onto the floor. In case one, the ball bounces back. So it comes in and it bounces back up. In case two, the ball sticks to the floor, does not bounce up. In which case is the impulse given to the ball by the floor is the biggest. Now remember, we discussed this before. In this case, we started with a momentum in the negative direction this way, and we ended up with a momentum this way. So the impulse by the floor on the ball to result in that change in momentum is going to be a positive momentum minus a negative momentum. I mean, this is final, this is initial, and this is negative. So that adds up to a large positive number because minus a negative is a positive. However, here we start with P initial down and we have 0. So it's 0 minus Also, P initial is, of course, negative. So here I have a bigger impulse than here. So case 1 is the answer. Now, in both cases, the direction of the impulse given to the ball by the floor is the same. What is the direction? Going back to the graphic, so I will not have to do it. So what does the impulse do? It's going to change the momentum from a downward momentum to an upward momentum. Or look at it here. It's PF minus PI. What do we get as a number? We get a positive number in both cases, telling us it's in the upward direction. Okay, you drop an egg onto the floor or onto a thick piece of foam rubber. In both cases, the egg does not bounce. Of course, on the floor, so this is foam, this is the floor. So this is our egg, this is our egg. Here, when it arrives here, it's going to end up in pieces. Here, it's going to be whole. In which case is the impulse greater? Okay, we drop them from the same height. They should have the same speed when they reach either the floor or the piece foam of rubber. So they should have the same momentum just before hitting either one. And then, what's their final momentum? Okay, so we said their initial momentum is the same. Their final momentum is going to be the same, 0, because both of them are going to stop. So the impulse is the same, since they start up with the initial momentum and they end up with the same final momentum. Okay, Fred, 75 kilograms, and Jane, 50 kilograms, are on skates facing each other. Jane then pushes Fred with a constant force of 45 newtons for 3 seconds. Who will be moving fastest at the end of the push? Fred, Jane, or the same? Now, this is probably, I should have broken this into several questions. Now, this is the force that Jane is going to apply on Fred. Now, if she's going to apply this on him, then, because of this force, Fred is going to accelerate. What's the acceleration of Fred? It's going to be 45 newtons over 75. And he's going to be accelerated for 3 seconds. So he's going to have a particular acceleration. Now, because she's going to apply a 45 Newton force on Fred, Jane is going to experience the same force for the same amount of time, 3 seconds. So then, what would be the acceleration of Jane? Again, 45 newtons, but now it's over 50 kilograms, not over 75 kilograms. So it's 45 over 50 kilograms, which is a larger acceleration than the acceleration of Fred. Both are going to accelerate for the same amount of time, meaning that Jane is accelerating with a bigger acceleration for the same amount of time. So Jane must reach a higher speed at the end of the push. Okay, other questions I could have asked here: who undergoes the bigger change in momentum? And actually, it's the same for both of them. That's conservation momentum. The initial momentum is 0 for both of them combined. So whatever Fred gains in momentum, Jane has to gain an opposite momentum that's equal in magnitude. Be careful about that. Now here, so we have a mass and it exploded. They tell us this is what's before. And they are asking us which case is correct, this or this. Now, of course, it is this case, case B. Why is it case B? Because case A has a momentum along this direction that's not accounted for in this direction. And remember, we started up with a momentum that's equal to 0, so the overall momentum at the end should be 0 in all directions. So if I have a momentum here, it should be cancelled by another momentum in that same direction. Like here, this momentum is cancelled by this. Now in this case, this momentum is going to be cancelled a little bit from here and a little bit from here. And these two momenta, they both have motion along this direction, so they both cancel out along this direction. So case B is the correct one. Okay, consider the situation. A ball moving at a speed v is brought to rest. The same ball is projected from rest, so it moves at a speed v. The same ball moving at a speed v is brought to rest and then projected backward at its original speed. Okay, so the first case, it's moving at v, we stop it. Second case, it is not moving, we made it move at a speed v. The third case, it is moving at a speed v this way, we got it to move at a speed v this way. In which case does the ball undergo the largest change in momentum? Okay, of course, 1 and 2 in magnitude, they are the same. We start with mv and go to 0. We start with 0 and go to mv, so the change is the same. Here we start with mv and we go to mv in the opposite direction. So we end up having twice mv as change in momentum. So, so case 3 is the correct answer.